Welcome to the CQSE seminar. Okay. Yeah, today our speaker is Professor Zinn-Justin from Saclay, France. Okay. Professor Zinn-Justin is an outstanding theoretician, as you know, okay, and also a member of the French Academy of Science. And he also have not many outstanding service to the community. For example, the director of the Theoretical Physics Division of the Saclay, and also the director of this fundamental research institute of the law of the nature. Okay. Yeah, and also the editor of the Journal of Physics A for a long time, and the director of the Infinities Summer School for a long period. Okay. So it's our honor to have Professor Zinn-Justin to give a talk. Okay, his title is From Infinity in QED to the General Renormalization Group. Okay, let's welcome Professor Zinn-Justin.
Thank you, Ting-Wai, for this kind introduction. So I'm not going to, of course, as you see from the title, to speak about really very new physics, but it's since Ken Whitson passed away not a long time ago, I thought that to revise a little bit some general ideas where the contribution was essential was appropriate. Okay, so it's not only a seminar on history of science, but I think that there are some ideas who, even though they're not so recent, they are still very worth emphasizing. So first, of course, the things not surprisingly, knowing my background, I want to emphasize is that quantum field theory, even now, and even though it has been invented in around 1930, so it's about 8 years ago, is still very much with us because it is the main theoretical framework to understand the physics of systems which have a large number of degrees of freedom and with a short range of local interactions. It can be quantum field theory, it can be statistical field theory, which means quantum field theory in imaginary time. But nevertheless, it's one of the important concepts of the 20th century, which will still guide us for a long time. And the other concept is that going with quantum field theory was the development of renormalization group. And renormalization group and quantum field are extremely linked. One cannot understand one without the other. It's not two different pieces of something. It's really one thing. Except that renormalization group has more general aspect than quantum field theory, or at least it forces to think about quantum field theory in more general terms. Indeed, as we know, quantum field theory we have discovered. I mean, first it has been designed to describe the physics of fundamental interaction at microscopic scale, and the recent discovery of the Higgs particle shows that now the standard model of particle physics is complete, and indeed describing up to 1 GeV at least completely the physics, fundamental physics of fundamental interaction, and it is based on quantum field theory. But something we learned in the 70s, a little bit later, which is about 40 years later after the birth of quantum field theory, is that it also describes the physics of continuous phase transition in a macroscopic world. So it's not microscopic physics, it's macroscopic physics. I mean, something you can see within their eyes. And we have learned that if we're interested to study the physics, to understand the physics near the critical temperature, near the transition point, in many systems like liquid vapor, ferromagnetic interactions, superfluidity, binary mixtures, then we can use quantum field theory, or we have to use quantum field theory. It also describes the properties of dilute quantum gases. Beyond, if you go beyond the Bose-Einstein condensation, you have a small interaction. Then you immediately go to discussion using quantum field theory, at least for again large distance properties, macroscopic properties. Describes statistical properties of polymer chains, avoiding random walk, percolation, and so on. So it's really one of the main theoretical tools of modern physics. As I said, it's the framework in which we can discuss strongly interacting, fluctuating degrees of freedom, provided the interaction between the degree of freedom in some sense is local, which means otherwise, of course, if you have some non-local interactions, then you can do at large distance what you want because you set it up like that. But here, it is large distance. The key concept is that it's large distance physics, which is created by cooperation of many degrees of freedom which only interact locally. Now, the birth of quantum field theory was not easy because the first calculation, which was our first calculation is 1930, but first correct calculation is 34, showed that a lot of physical quantities, when you calculate, you got infinite result, which of course in physics is bad. And eventually, one found a cooking recipe, just an empirical recipe, which we call renormalization, which was a way of managing infinities in such a way that you can extract finite predictions. Now, when I was a student, that's exactly what you would learn. That you would learn the recipe of renormalization, but you were not supposed to question why this was appropriate to do, and what was the meaning of it. And actually, many physicists, mathematical physics, wanted to hide this completely because it was embarrassing. It was logically, not logically founded. But on the other hand, since Shelter Island, or shortly after Shelter Conference in 1947, we knew that it agreed with experiment, and of course, the final decision always comes from experiment. From experiment, you can say it's agreed and but I remember even in 1968 at a large conference organized by Abdus Salam at ICTP in Trieste for the inauguration of a new building where all the stars of physics had been gathered, that Dirac would say that it's clear that quantum field is wrong, and that due to infinities, and then he started even questioning quantum mechanics and say, like Einstein, I started wondering whether quantum mechanics is not a failure. So it means really that it was a somewhat embarrassing situation. Now, in fact, a new concept, which is renormalization mode, which was first abstracted from formal properties of quantum field theory, but which was abstracted and not understood either. And I can testify of it because I had many conversations with Mr. Cherkov, collaborator of Bob Lyubov, one of the group involved in discovering this renormalization group, and even now it doesn't understand renormalization group, except as a kind of mechanical tool. Okay, so it means that really there was not a real understanding why, except that it were, again, it was an algebraic property, what was so real of it. And I think that the meaning of renormalization was only slowly fully understood in the context of continuous space transition. And in this aspect, the contribution of Ken Wilson was absolutely essential because he knew, of course, being a student of Gell-Mann, about the technical renormalization group of quantum field theory, but he understood much deeper what was the real meaning of it. And I think that it is one of these absolute, amongst not the only outstanding contribution. There's also lattice gate theory, those things, short distance expansion. But I would think that in the long term, he will be mainly remembered for that. And now the outcome of this is that a better understanding of renormalization group idea finally led us to a satisfactory integration of renormalization process in quantum field theory. Okay. And the consequence, which may be perhaps disappointing, is that in our modern viewpoint, quantum field theory is not a final theory of anything. It's just some low energy approximation of some more fundamental theory which we don't know about. Which is something which is peculiar in the sense that if you go in the past, we have constructed many theories which Of course, there are approximation, but we know the approximation because we have some physical insight about that. But we don't know that they are approximation because they are mathematical failures. Quantum field theory is a mathematical failure, and it doesn't stand alone. Also, so I'm not very interested and enthusiastic with people who want to show that QCD, renormalized QCD is a consistent theory, because the standard model itself has no chance to be a consistent theory, and therefore I care little about the mathematical question about whether renormalized QCD is, because we know that eventually quantum field theory will fail anyway. Okay, so it's not an interesting issue, or at least it's an interesting mathematical issue, but not an interesting physical issue. And I mean, if you consider, by contrast, you consider gravitation, the law of gravitation by Newton, you can make a consistent theory of the law of gravitation. I mean, it's not a mathematics which tells you that it's wrong. You know that it's just an approximation, but otherwise it's totally consistent. Yeah, well, quantum field theory in itself already declares, well, I'm a temporal theory. I cannot become mathematically consistent. I will fail at some energy, at some length scale, but we don't know which one. And this is one of the important modern issues. Now, the problem started in about 1930. I mean, it was after Dirac equation showed that one could incorporate relativity in quantum mechanics, because before that there was the obstacle that one didn't know how to make consistent relativity in quantum mechanics. And then it's there where the whole problem started, which is about 1930. So the thing one has to always remember, it is that quantum electrodynamics is not like in quantum or non-relativity quantum mechanics, it's not a theory of particles. Okay? So that, and even now we can discuss with some colleagues, they are not totally, I mean, they are aware of it, but they don't fully realize it. It's not you just don't put together some individual particles and the interactions. It's not true. Okay? So it's fundamentally different from the relativistic quantum mechanics. It is a quantum field theory, which means that it is a quantum extension of a classical field theory. And the dynamical values are not particles, they are fields, okay? Which in the case is electrometric and magnetic field. Okay? Now, as a result, as a consequence, such a theory is very different from a theory of particles because it involves infinite number of degrees of freedom. And in this case, strongly coupled. It's not a free field theory, so the degrees of freedom are strongly coupled. Okay? And they are fluctuating. That's our quantum fluctuation, of course, in this case. Okay? And which is due to the fact that data for field is the value of the field at each point in space. Okay. And that's what you are evolving. Okay. And in particular, we know it because, I mean, even if you wouldn't know about all that, you know that there is no conservation of the number of particles in high energy scattering. And any picture of LHC event will tell you so when you discuss to lay people, sometimes they have the feeling that it's because inside the proton is all these particles sitting inside the proton, and when they collide, they come out like a little bit like the picture Feynman was giving, that high energy scattering is watch scattering, and then you see all the piece of it. It's totally wrong. They come from the vacuum. They're not sitting inside the proton. Okay? So it's not that you just detect the inside of the proton. Inside the proton, you just see some quarks and gluons. Nothing more than that. And it depends even how you probe them. Okay, so that's oh, I did something wrong. Let's see. No. You see, I learned Chinese slowly. Microsoft Chinese. Okay, now the important aspect is that quantum field theories, is those which describe microphysics, but also those which describe critical phenomena are local, which means that it's a generalization of the idea of point-like particles. In fact, it's point-like particle with contact interactions, if you want to be precise, but this is a way of wording because it's really a quantum field theory, so it's just a way. But the important point is they have no short distance structure. Yeah? And the reason that they have no short distance structure is that when you think about it, it's very difficult in relativistic theory to give a structure to something. Yeah? You can build it from some interactions, but some object which initially would be some kind of sphere or whatever is not very consistent with relativity. So we don't know how to do it. And in fact, the only proposal we had came much later with things. And it is this combination of infinite number of fluctuating degrees of freedom, which some interaction, and combined with locality, which are the basic reason why quantum field is such a complicated object, with some bizarre properties. Okay, now just for the fun of the younger you and the older one, they know about this, but the younger maybe that read every day such textbooks about history of science. Just let me remind you very shortly very rapidly. Okay, so the Dirac equation is 1928. The work of Heisenberg and Pauli is 1929, 1930. Again, it gives you the time frame. And the question was to calculate the first quantum correction to the classical theory of electromagnetism, and in particular the influence on the spectrum of the hydrogen atom or things like that. So the expansion parameter is a pure number, which is fascinated many of our colleagues, theoretical colleagues, for some time, which is a fine structure constant, except that now that we know that it changes with scale, we are no longer so obsessed with its value. And so the question was to calculate the correction to the electron propagation in a photon field. And so there were two permutations of Oppenheimer and Bada, and both were wrong. Still wrong. And the reason is that the motivation to do this calculation initially, at least, there's something, some noise, yes. The main, one of the motivation, there were several motivations to do that, of course. But one motivation was to cure the disease of the classical relativistic model of the point-like electron. Thank you. Okay, nothing to work. Thank you. The reason is that in a relativistic theory, you have to incorporate into the mass the self-energy. And therefore, you have to consider the self-energy of an electron acting on itself in the presence of electromagnetic field. And now, you all know that, it's a trivial calculation that if you imagine a sharp sphere of just R, then you get an Coulomb energy which is E square over R, and this clearly diverges when the radius goes to 0, and therefore there is no consistent model of the classical electron in relativistic theory. So the hope was to cure this disease due to quantum fluctuations. Okay. So the calculation is elementary. Now every student, at least in particle physics, does once this calculation, takes a few minutes to do it. But this was a time where there were no Feynman diagrams to speak of. And in addition, people were using non-relativistic perturbation theory. In 1930, the positron had not been discovered, so they didn't know what to do with the negative energy scales of the Dirac equation, whether it should be incorporated or not. And in addition, there was a question of gauge fixing, and they didn't know what to do with gauge fixing either. So to explain why even famous people like Oppenheimer did it totally wrong. Okay, and finally, it took 4 years to get the right answer. And it's, of course, has a logarithmic divergence, as you know. So the answer was that instead of a linear divergence, there was still a soft logarithmic divergence, but it was still divergent with some scale, which is no longer the radius of the electron, but which is some scale of the form of the interpol. Okay. So, and not only you discover that it's wrong, is that it is infinite, but when you think more deeply, you understand that if you put together locality, which is point-like particles and contact diffraction, and unitarity, which is conservation of probabilities, then you cannot avoid this locality divergence. Because I said, yes, there is no scale in the problem. And the second is that due to unitarity, all the process which is emitting, absorbing a photon, all contribute in an additive way, so there is possible cancellation. Okay. So you are out of business. And the answer is that, which was become obvious, is that quantum dynamics is an incomplete theory. It's not something which can stand alone, but nobody knew how to change it. Of course, the idea you have naturally is to introduce some cutoff somewhere, but if you introduce a cutoff, then you destroy some fundamental physics property. For instance, in the natural way we now call Pauli-Villard regularization, then, as Dirac proposed in 42, you abandon unitarity, but unitarity conservation probability is very well established, and so you are very unhappy to do that, so it doesn't seem to be the right thing to do. And second, the other way of curing the disease is to introduce a small length, as proposed by Heisenberg in 38, and also later by Wheeler. But in a relativity theory, you don't know how to do this either. Now the only candidates which were eventually proposed are string theories, but this game is no longer of the form of a quantum field theory. It's some non-local object based on strings, and it was invented much later. Okay. At this point, Wheeler and then also Heisenberg proposed to abandon quantum field theory whatsoever, and to replace it by a theory of physical observable, which are in this case scattering data. And it's called, what became known on this name of S-matrix theory. And this kind of desperate idea, because you give away a lot of what you know, became very fashionable when I was a student in the 60s, in the theory of strong interactions, and which respond for strong nuclear force, and was only abandoned once Quark was discovered. And the reason was that in strong interaction, perturbation theory didn't work because the interaction were too strong. However, those who really wanted to save quantum field theory, or they thought that there was something in quantum field theory which should be understood, went on to try to characterize this divergence, understand why it diverged, where it diverged, and things like that, and they calculate quantum correction. And one remark which is still worth remembering is a remark which appears in the paper of Vicky Weisskopf, which is one of the great men of quantum physics, which was not recognized by the Nobel Prize, and I think that was wrong to have not done it. But unfortunately, his big work was before the war, and quantum field theory developed after the war. He noticed that something which is clear, okay, we know this very well now, but at the time it was not, that he studied infinities to all orders, actually, and he realized that in the case of charge fermion, the divergences are always logarithmic, which, if you think that there is some cutoff provided by some other theory you don't know about, is acceptable. It just means that you cannot calculate the correction, but it is a small number, because log of some ratio, and at the time people thought that maybe strong interaction would provide a cutoff, so it would be 100 MeV, typically the mass of the pion. That's acceptable. It just tell you there is a small correction, but we don't know how to calculate it. However, if you apply it to charge scalar boson, then you get this quadratic divergence, and then that's totally unacceptable. Numbers are you destroy the classical theory. And after that, for some time, it was known as a folklore among the quantum field theory, not me, but the generation before me, Zinn-Justin like that presumably scalar bosons should not be incorporated as fundamental part of the theory. Now this problem, as you know, is still with us. The reason is that physics decided otherwise. Standard model has now been completed by the discovery of the Higgs boson, announced July 4th, 2012. There's a mass about 125 GeV. It is a boson, and more recent analysis of the data show that it seems to be a 0+ scalar particle, so it has a proper quantum numbers to be a candidate, and this has been discovered by assuming that it's now very likely, I mean, everybody believes that we have indeed found the Higgs boson, and so the model complete, and it has as a fundamental ingredient a scalar particle. Okay. Now, so that this will be confirmed, but there is now little doubt about it, and therefore, if this is true, then you again ask the question, what will be the nature of the cutoff? Now, if, and there's some indication that in principle the standard model could be valid up to something like quantum unification energies, or maybe the Planck scale, or something like that. If this would be true, then you face a fantastic problem of fine-tuning. It will be the second fastest after the cosmological constant, largest number in theory. And this is a famous fine-tuning problem. Now, theorists thought that they could solve it by introducing supersymmetry, because this introducing a symmetry between boson and fermion allows to cancel the quadratic divergence of the boson, scalar boson. Unfortunately, somebody aware that no supersymmetric particle has been found at LHC yet, and presumably will not be found in the data which have been recorded. And so, if even if supersymmetry exists, but if it's pushed to enough high scale, then this problem will come back. Okay, so that's an important issue, and we don't know about it. Okay, so maybe the second phase of LHC will tell us something about that. Hopefully, it will give us some indication. Okay, now, I come back to the far past, okay, and then in 1936, by exploring all the divergences, what became, it's always one loop calculation. It's the leading quantum correction, okay, when people didn't start calculating two loops because there was no point. Didn't know what to do with anyway. Okay, now, some people, after calculating several physical observables, realize that if you subtract two observables, sometimes you always find the same kind of divergences, maybe they cancel. Yeah, but well, nobody knew what to do about it. Now, the major change happened in 1947. There was a conference after the war in Shelter Island, which is not so far from Long Island. And in this conference, all the stars of the time came. And several experimental results were presented, one by Lamb and Rutherford, who measured more precisely due to technical development during the war in the radar system, the splitting between two levels of the hydrogen atom, 2s1/2 and 2p1/2, and also the Rabi proof in Colombia had measured the anomalous moment, magnetic moment of the electron. Okay. Now, the folklore says that a bit in the train back to Cornell made just this calculation of subtracting two physical quantities, and with a cutoff, something, a very rough calculation, and it found more or less the right answer, the value of the lamp shift. And sometime later, not far later, Schwinger obtained the leading contribution to anomalous moment, magnetic moment electron, and with the same strategy by subtracting divergences, and it worked again with experiment. And by then, of course, it became clear that there was some physics in doing this kind